Hi everyone, how's it going? My name is Carl Diaz with the Learning Resources Center here at the University of Colorado, Denver. And today we're going to talk about static fluids. So let's get going here. So before we get fully into the idea, I think it's good to talk about what a fluid is to make sure that we understand that idea, and then we can talk about everything else. So a fluid is any substance that can flow and change the shape of the volume it occupies. Okay, where if you're trying to find some contrast to that, solids typically can't, right? Where liquids take the volume shape of the container they're in, essentially, right? That's what fluids do. And we in physics we categorize these this idea of fluids into two ideas, so liquids and gases, because a lot of people, when they think fluids, they think liquids, but in physics we are talking about liquids and gases. And so what's the difference there? Well, liquids are molecules that are very close together, that exert a lot of intermolecular forces, hydrogen bonding, stuff like this on themselves. So they stick together, right? So when you go to, like, for example, like pour water out of a cup, all the molecules stick together. They all flow out together, right? Where with gases, the molecules are a lot further apart. There's intermolecular forces between the molecules, but they're not very strong. And so they tend to not stick together as well. That's really the difference. So essentially, if you have a container, a sealed container, let's say some sulfur gas in a sealed container, and then you take the lid off, well, then you can start to smell it. And the reason why is because the gas inside there, right, the sulfur gas, it's not bonded to anything specifically inside the container, so it's able to move out and take the volume of, if you open up the container, the gas is able to escape and expand into the larger volume of the room that it's in. So essentially, both these things, occupy the volume of the container that they're in. It's just, one of them sticks together a lot better, is a lot more attracted to itself than the other. But in this class, we're going to be talking about ideal liquid and gases. So essentially, they're going to work the same way. They pretty much, when we say ideal, when you exert a force on either a liquid or gas, there's no compression. And with liquids, you don't see much compression normally, but with gases, since there's room between the molecules, when you first press on the gases have to come together before that force is actually exerted on the gas to cause some sort of change in motion. So the liquids tend to not be as compressed. Liquids are compressible, but they tend to be not to be as compressible. But in here, we're talking about ideal liquids and gases. So neither are going to be compressible. No compression here. They're going to all kind of work the same way. But that's just the difference between the two. Like I said, it's good to know, but definitely not the focus of what we're trying to talk about here. So here, right, I just wanted to make sure that we understand the difference between mass and density, and give us a reminder of what pressure is, right? So mass, keep in mind, is the amount of matter in an object, right? And there's an equation for it. You can see it there. You see it's density times volume, and we'll talk about that here, because that's not going to make much sense if we don't know what density is. But mass is more about how much stuff an object is made of. So the mass of an object cannot change just as long as the object remains intact. That's what this is saying, or it doesn't break apart. Essentially, like, I have a certain mass, my body, right? But if my arm falls off, that's going to change my mass, because I've lost some of the atoms and things that, in some of the volume of my container, right? So that's the difference. Mass is essentially, doesn't have to be just one molecule. Mass can be, a bunch of different molecules. I'm made of my mass is made up of different carbon and oxygen and nitrogen, stuff like this, right? Where each one of those molecules has their own density, right? And that's what's different difference between mass and density. So what's density? Well, density is like a fundamental property of matter that tells us how much of a specific type of atom we can fit in a volume container based off the size of the molecules that make up a specific kind of matter. So essentially think of like carbon and like iron. Iron is much larger than carbon, has way more electrons. And so we can imagine iron is a big giant ball and carbon is like a tiny ball. Well, let's say I handed you two containers of the same volume, same size, and I told you how many iron balls can you fit in there versus carbon balls. Well, you'd be able to fit way more carbon balls in the container than iron balls because the carbon balls are smaller, carbon's smaller than iron. And so essentially, right, that's the difference in density, right? The carbon's a lot more dense. I can fit a lot more carbon in a container than I can iron. Okay, so we want to think about this, all right, and think about how these things come together in terms of the difference between mass and density, okay? And mass also, and we talk about it in physics, it's also part of inertia. That's not quite how we're trying to refer to it right now. We're really just trying to talk about the amount of stuff something's made up of versus density, where all that stuff that something is made up of, the individual parts will have their own density. They're all going to be able to individually have their own sizes and be comparable. So, and so what's, and again, there's an equation for density too, if you need it. I have it right there, which is the, mass per unit volume. So, we're going to use that in here coming up. So, just keep it in the back of your head, but know there's an equation. And then know that pressure, right? Remember pressure from when we talked about deformation. So pressure isn't directly related with fluids at all. Pressure just has to do with the amount of force per area, specifically the normal force per unit area, where I have here, right, the normal force, right, is the force like perpendicular, right, to a surface. So pressure is the force, that's being applied perpendicular to any surface, which is what I'm trying to show right here. But it's best to just, if you were to look at the definition of pressure in a book, it would say the normal force per unit area, but just think of it as the force per area, and that force is always going to be perpendicular to the surface, okay? Pressure is not a vector. It doesn't have a direction because its orientation is just really based off of the object, the object's orientation, or the surface of the object's orientation. But the force itself has a direction, right? And so that's the vector here, but pressure is not a vector, nor is pressure a force. It's the amount of force per area, right? And how does that fit into what we're talking about here with fluids? Well, just keep in mind that each like if you're right now, you're probably sitting in a room, right? And it's filled with air, hopefully, and oxygen, right? And so you have a certain surface area to your body, right? Well, all the individual molecules in the room are hitting the surface area of your body, all of them, billions of them, right? And we could go in there and we can count all those molecules and all the individual forces from those molecules and add them all up, right? And that would give us a good answer, but it's very difficult to do. Or we can look at just how much force per area. We can look at how much force those molecules apply per certain area rather than looking at all the individual forces of the individual molecules themselves. So that's how pressure plays an idea into fluids and specifically liquids and gases. And also know that you can solve the pressure equation. If you want to know the force associated with the pressure, you can always solve the pressure equation for force, and you can always find the force associated with a certain pressure. But pressure isn't a vector, force is a vector, and pressure is not a force, right? Force is force, pressure is force per area. All right, so now that we got those things out of the way, let's get into the nitty gritty. So static fluids, what the heck is a static fluid? Well, the best way to think of a static fluid is a fluid at rest or equilibrium, okay? Or in terms of Newton laws, it's when the net force on the fluid is equal to zero. So one way to tell is if the liquid isn't moving. The liquid isn't moving, then there can't be any net force on it, right? Because then it would be moving and speeding up and slow. Not maybe, and maybe the liquid may be moving, but if it's moving at a constant velocity, then we also know that the net force is zero, right? But right, when we look at fluids themselves and just see them in a container, that's the best way to recognize a static fluid because it's at rest. It's not moving. There's no flow, right? Relatively, if we look really close, right, we would see let's say it's water, right? We would see all the individual water molecules moving around, right? But the fluid itself, the net force on the fluid as a total itself is equal to zero. So, and again, it also works on the principle of Newton's, third law. So, like if you think of this container right here, right, the fluid inside. Let's say there's fluid in here. I didn't draw it, but let's say there's fluid in here. It's exerting a force on the walls, right, and that. Right. And so the walls are exerting a force on the liquid. And so these forces right here, right, that are being exerted on the, let me do that in a different color. These forces that are being exerted back on the fluid, right, are equal and opposite. So and this is a closed container, so this liquid is in equilibrium. I mean, that's another way to look at it, right? Some forces right here are equal to zero. And that's what that's the main definition of a static fluid. So we want to look at static fluids, right? The rest of our discussion is going to be based off static fluids where the net force is zero. And that's really the main idea here. So let's keep going. Versus where, again, if you need like a comparison, where fluid flow is where the net force isn't zero. Okay, there's some net force on the fluid due to some change in pressure, and so that fluid's gonna flow. Okay, so static fluids, no net force, fluid flow, net force. Okay, so that's how you can kind of break it up in your head. If you're like, why are these people teaching us this right now? Well, static fluids let us look at equilibrium situations. Fluid flow lets us use and apply Newton's second law a little bit more. All right. So before we get going, or I guess, well, yeah, to begin our discussion, one of the best things to talk about, because I think it's obvious. I guess the thing to say is it's obvious to look at a fluid in a container and like I have drawn here, right, a completely sealed container, and say, oh, okay, well, the forces, right, the fluid's exerting a force on the container's exerting a force back on the fluid, and so it's a very easy situation to be able to tell that net force is zero. But what about other situations? Well, in order to describe those situations, we got to first start with the discussion of atmospheric pressure, because what if I have a container that isn't in a sealed or fluid that's isn't in a sealed container? Like, how does that relate to no net force still? Well, that all has to do with atmospheric pressure. Essentially, and again, when we say atmospheric pressure, yes, it's directly related to the Earth's pressure. But remember, the atmospheric pressure of any system could be whatever the atmosphere, whatever the pressure is surrounding, right? Because we can run a lot of experiments where we can put a container in a vacuum or something like this, where we can take all the pressure out, right? So and then the atmospheric pressure in there would be zero if it's a vacuum, right? And so think about that. And so when we bring in atmospheric pressure, we're really just trying to talk about the pressure of the environment that the fluid's sitting in. But for this class, we don't get into a heavy discussion of fluids. So atmospheric pressure, right, just as I got stated here, is the pressure of the Earth's atmosphere, or the pressure at the bottom of the sea of air which we live. Okay, so I know it sounds like sea of air, but I'm not talking about the ocean, right? The air that we live in is a sea. Like it's just like the water in an ocean or in a lake. It's just less dense, but it's still an ocean. We still live in an ocean. It's just an ocean of gas, not an ocean of liquid. All right, and so the atmospheric pressure, right, is the pressure, right, which is the force per area associated with you know, the Earth's atmosphere. That's the best way to think about it, okay? And that pressure varies with weather and elevation, right? We know at the top of a mountain, the pressure is a lot less. We know at the bottom of a mountain, right, atmospheric pressure increases, right? And then I don't know if you've heard during weather reports, but they constantly say, oh, you know, high pressure, low pressure systems. So those are all talking related to atmospheric pressure and changes in atmospheric pressure. So it doesn't remain constant. Uh, 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 and when we talk about a number for it, we're really looking at like, so this is normal atmospheric pressure at sea level, which means like no storms or anything like this, right? So just typical nice day atmospheric pressure at sea level is this number. Now we use this constant a lot, just like we use, you know, how we say like G is equal to 9.8, even though it changes as we move from, you know, elevation from the center of Earth, right? It definitely changes. And so this is just an average, just like this ATM is just an average, right? And I should have, I don't want you to get confused, but this atmospheric pressure value is just an average where, you know, it's 1.03 times 10 to the fifth pascals. That's one way, where a pascal is a Newton meter squared. Or, you know, because we're here in the United States, it's always good for you to hear this. So, you know, one atmospheric is equal to 14.7 pounds per square inch. Okay, so you know, that might give you a better feeling of it, but we don't use those units in here. Pascals is Newton meters. Okay, cube or squared, right? That's what a Pascal is. It's best just to write Pascal, right? We don't use pounds per squared inch. And so that's a number you're going to generally use if you need a number for atmospheric pressure. Like, you know, we don't expect you to go outside and measure the atmospheric pressure at that particular moment or something like this, even though it changes. So what does that have to do with anything? Well, atmospheric pressure kind of relates to like pressure at a certain depth. So when the atmosphere pushes on the ocean, right, it's going to push on it and kind of, I hate to use the word squish, but it does. Like you know, it's gonna, the bottom. There's a bottom of the ocean, right, which is the you know, ground, right? And so the atmosphere is pushing down on the fluid, and the ground is pushing up on the fluid, right? And so the 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 uh, liquid itself is going to kind of, you know, set up in terms of a certain density, and so that it helps, it helps form a uniform density in there is what it does in a sense. But don't worry about that so much. I just, you know, it's good to think about. But pressure at a certain depth. So what's going on? So we know that the atmospheric pressure right at the top is pushing down on a container of fluid, right? The container of fluid has a point where the liquid starts and where the atmosphere begins, right? And so the atmosphere, the air around that liquid is going to push down on it, right? And then what's going to happen? Well, as you get deeper and deeper and deeper, right, more and more of this water is going to start to add up and have some sort of weight to it, right? It's going to start to weigh more and more and more the deeper you go. And so you have these forces starting to push down on you, right? Well, these two forces, right, since the and this changes, right? I mean, this is based, let me do it in a different color. So as you get deeper and deeper, right, there's more and more water that starts to sit above you, right? And then this water here, right, is all going to have a certain weight to it, right? And then as you get deeper and deeper, eventually, right, that water, right, and the weight is going to be pressed all the way against the bottom of the ocean. And so what happens is that these forces end up being in equilibrium, because how do we know? Well, the ocean isn't being pushed up and the ocean isn't moving down, right? So we know that these even though, you know, there's all these forces on the fluid itself, we know that because the fluid isn't moving, that the sum of forces are equal to zero, right? And again, this is something that you should know from Newton's first law, right? It's something we recognize. If an object, and if it was flowing at a constant velocity, then we'd also know that the sum of forces were zero. But here it's not moving at all. It's just sitting in a container. So we know that these are the forces on the fluid, right? But they are all going to balance themselves out essentially, right? So if we wanted to write a equation, we have the force from the bottom, right, minus the force of the atmosphere, right, minus the weight of the fluid, and those all are going to be equal to zero. These are going to balance. Everything's going to be balanced themselves. Essentially, the force from the bottom, right, is going to be equal to the the force from the atmosphere on top, plus the amount of weight of fluid that's going to be pressing down on the bottom. That's what that equation is telling us, okay? So, and then right here, that all these forces, right, that we talked about here, they're all, well, they end up balancing themselves out is what we should say. We shouldn't say equal and opposite. We should say they end up balancing themselves out, right? We should say balance. These forces. That's a better way to say it. So all these forces here end up balancing out. Okay, and then I just drew a little picture of what's going on top, right? The force is essentially, right, the atmospheric forces being, right, it's pushing down, right, all along the top. That's what I'm showing here. And then the bottom, the ground is pushing on all along the bottom of the fluid. So I just wanted to show you a close-up view just to make sure you understood what I was talking about there, but that's what's going on there. So again, these forces are going to balance out. Again, maybe not equal and opposite. Some of these forces will balance and be in equilibrium. Okay, these forces follow Newton's first and third law. Okay, so, you know, the reason why this force from the bottom is there is because the water's pushing down on the floor, right? Or the ground, whatever it is, the bottom of the container, whether it's the ocean or just a cup of water. And then the container's pushing back because pushing back on the fluid because the fluid's pushing on the container. So that's following Newton's third law. And then first law is the equilibrium idea. Okay, so these ideas follow Newton's first and third laws, okay? And then the last thing we know is any pressure at any depth is a combination of the surface force, the weight, which is essentially, I'm just reiterating everything that's in this picture here. So any pressure at any depth is a combination of the surface force, right, which is typically the atmospheric force or atmospheric pressure, right, the force from the atmosphere, right, the weight of the volume of the fluid, okay, above a certain reference point, right? So that, like we said, the deeper and deeper you get, the more water is going to be above you, right? So that water that's above you has a certain weight that's going to press down, right? And then the upward force coming from how much the water is pressing up against itself, or if you get to the bottom of the ocean, then how much the ground is pushing back up on the water. So the reason why I wrote it like that is coming from how much the water is pressing up against itself, is because, like, if we were to look right here, let's say we didn't get, you know, to to the ground. Well, this is still going to be a combination of the weight of the fluid above it, the atmospheric pressure, the force from the atmospheric pressure, right? And then instead of the force from the bottom, there's still going to be a force up, but it's going to be the force from the water pushing back up, right? The water's pushing down on itself. The weight of this water right here, it's in this amount, is pushing down on this amount of water. And so this water is what? Pushing up. And so that's going to be that force. It's going to push back. So, but if it's all the way to the ground, then the ground's going to push back on it, right? So either way, however you want to look at it, right? So again, any pressure at any depth is a combination of the surface force, the weight of the volume of fluid above a certain reference point, and the upward force coming from either how much the water is pressing against itself or the ground. The fluid. I keep saying water, but I should be saying fluid. So that says, or the ground that the fluid is pressing on. Okay. Okay. So, yeah, I don't know why I have water in here. I'm using fluid everywhere else. There we go. Okay, so let's move forward. I just want to make sure that you understand this. This is really important because it has to do with everything else that we're going to talk about here. So pressure at a certain depth, how does it work? Well, like I was saying, and so I have this little picture over here because I wanted to kind of give you a good idea whether, you know, we were talking about you know, in the air or on the bottom of the ocean, how this was working. I wanted to make sure that you understood this idea. So like I was saying, we could look at the air, right? The air is going to have weight, right? As you get deeper and deeper and deeper and deeper and deeper and deeper, right? This much air, let's say, right, is going to have a certain weight to it, right? And that's going to continue to press down, down, down until it hits the ground, right? And so just like we were talking about before, right, the force on the air here is a combination of the weight of the air, the force at the top, and the force at the bottom, right? So that's definitely helpful, but it's best to look at something that's going to make more sense to us intuitively, because it's hard to look at the atmosphere. It's hard to look at the air itself and you to get a good grasp of this. So what's better is to look at water, right, or the ocean, right? So we know that the atmosphere, right, itself pushes down on the ocean, right? And then, like we said before, the ocean itself, right, based off the volume of water that we're trying to talk about. So in this case, we're talking about this huge chunk right here, right? This huge chunk of ocean has a certain amount of weight to it, right? And that weight is pressing down on the bottom of the ocean, on the ground of the ocean. And so the ground of the ocean is pushing back on the fluid. And so what we want to do is we want to see if we can kind of relate, right? Build an equation that'll relate this depth, right? This depth that we're at to the changes in pressure that we feel as we get deeper, right? So what we do is we start by setting up an equation. So we have the force from the bottom, right? And we're assuming that positive is up, negative y is down, right? So all the forces pointing up will be positive, all the forces pointing down will be negative. So the force from the bottom is pointing up, right? The force from the ground is pushing up on the fluid, so that's positive. And then we have the force from the top, which is the atmospheric force in this case, or the force from the atmospheric pressure, right, pushing down, and then we have the weight of the fluid itself pulling down on itself, right? But like we said, we know that the ocean's in equilibrium. It's just sitting there, right, in its container. So it's essentially, even though there might be, flows within the container, it itself isn't moving. The ocean isn't lifting up off the ground or falling down through the ground or all traveling onto the land or something like this. It's staying put where it is, right? It doesn't move. So it's essentially at rest as a whole. And so we make it equal to 0. And then what we know is that force is equal to pressure times area, and that mass is equal to density times volume. So we kind of make those exchanges in this equation. And we say that the force at the bottom, since force is equal to pressure times area, can be the pressure at the bottom times the area, right? The surface area. And in this case, the area is going to be the area of the surface area of the ocean, right? So the ocean is going to have, a certain area associated. Let me do that in a different color. It's going to have a certain area, right, associated with it. That the surface area that the bottom is going to be pushing up on, and that the top is going to be pushing down on. And so those areas in this equation are the same, since we're assuming that we're looking at the ocean in this case as a cube, right? So the area is essentially the same. And then we make the exchange of density times volume in this equation for mass. Now, the reason why I'm doing this, a lot of times I don't show you proofs in my videos, but the reason why I'm doing this is because you need to actually know this math. This math is going to be helpful for you to know how to solve problems, because you see how I make exchanges. So you don't really have to know this derivation. What you should be paying attention to really is that, oh, okay, I see that every time Carl had mass, right, he switched it over to the density of the mass of the fluid is exchanged for the density of the fluid and the volume of the fluid, right? And so, and anywhere I had force, I switched over to pressure times area, right? And then what we do, right, what we can see is this, right, first of all, right here, this is the weight of the fluid, which is important to understand, because we see that we have these essentially the force from the top, and the force, the net from the force on the top and force on the bottom is essentially equal to the weight of the fluid, which is interesting. And we're going to use that here coming up in a second. And like I said, again, this derivation, you don't have to know so much. It's the math that's important. And then what I see is I have this volume here, and so I can make that volume exchanged out for area times delta y, or any kind of displacement. See, volume is equal to meters cubed, right? And area times displacement also has the units of meters cubed. Area is meters squared, right? Let me write that in a better place. So volume is equal to meters cubed. Area times displacement is also equal to meters cubed, because area is equal to meters squared and displacement is equal to meters. So when you multiply those together, that's meters cubed. So we can make that, we can exchange volume for area because they have the same units, which is what I'm doing here. Oops. Which then allows me to make that exchange. And then what I'm able to do is then all those areas, right, are essentially the same, right? The area of the fluid, the surface area that the atmosphere is pushing on the fluid, and the surface area that the bottom of the ocean is pushing on, right? Those are all the same area, so they can cancel. And I end up with this wonderful equation that relates the pressures, right? The pressures at the top, the pressures at the bottom of the ocean, to, or of a fluid to the depth at which we're at, right? Because we know that as we get deeper, simply because the weight of the water increases, or the weight of the fluid, let's say, in this case it would be water because we're in the ocean, but even in the atmosphere, the weight of the fluid above us increases as we get deeper in it. More and more of it is above us, and that weighs more, so it pushes down on us, right? We know that alone is going to cause a difference in pressure as we go deeper. And so we know this exists, this idea of like pressure being different at different depths. But this equation, right, definitely gives us the relationship between the two. And so what you'll do is you'll typically see this equation written as P2 and P1. So I have written right here that P bottom is actually P2 and P top is P1 in this equation. And that's typically, you see this equation written as P2 minus P1 is equal to density of the fluid. This fluid, right? And gravity and delta H is your depth, how deep you are in the fluid, where the top is, the initial height would be 0, and then your final height would be any depth that you're at in the fluid. And this equation is also known as the gauge pressure equation, which we'll talk about here in a second. But before we do, we want to kind of make sure that we relate one idea that we were talking about here. So this force that was coming from the top of the fluid, let's say, or even the bottom, but let's just talk about one force right now. But this is true for all of them. So let's just say the atmospheric force, right? The pressure from the force of the atmosphere, right? As it pushed down, that force from the atmosphere was actually felt all through, right? It's felt. That's what I was kind of showing you with this previous picture, is that it's felt all through, not just on the top, but all the way through the fluid, right? All the way through the fluid, that force, the atmospheric force is felt throughout the fluid. It just is, in this static fluid. And so that idea is called Pascal's law, right? Because that's what was going on. That's essentially the idea that we use to derive this idea of pressure and depth, right? Is we can see that for atmospheric pressure, that force is being applied at the top, but not just at the top, it's also being applied all the way through the fluid, because we have to include the force at the top at any depth that we're at, as well as the weight, right? That's what this equation was telling us, is that essentially, right, that force at the top is always included in sorry, I got my words twisted there. Is always included because it's still there no matter what depth you're at. So that atmospheric force from the top is always there no matter how deep you go, because it's part of the force that you're feeling at that certain depth. And so why is that? That's because of Pascal's law. So Pascal's law essentially is the pressure applied, when a pressure is applied to any enclosed fluid, it's transmitted, right, undiminished to every portion of that fluid and the walls of the container. Okay, so essentially I tried to show you some pictures here, right? So this fluid, right, is it's enclosed, right? It's in a container, and that top force, right, that atmospheric force, is being felt all the way to the bottom of the container, right? Even though it's pushing on the top, it's also felt all the way through the bottom of the container, right? As well as any weight of fluid above that certain height, right? That's what we just got to talk about. But this is more about forces being applied, not really the weight of the water. So we're talking about applied forces to the fluid now. So when atmospheric pressure is applied to the top of the ocean or applied to the top of a cup, that atmospheric pressure is not just felt at the top, right? That atmospheric pressure is felt all the way through the fluid. So if it's the ocean, the atmospheric pressure is felt, at certain depths, or is included in the measurement of the pressure at a certain depth, because it's part of why you feel the pressure you do at that depth. Okay. And no matter the container, even if this container, it's completely open to the air. So it's like, oh yeah, well, all the force is pushing down. So yeah, that makes sense that it's transferred all the way through. But this I have kind of like a bottleneck, right? But it still works the same. Some students think, oh, well, just the force that's in contact with the air is going to fill the atmospheric force. And then that's only going to be distributed as, like maybe just through this container. But that's not how it works. Even if the force is just through one small opening, that force is still going to be felt throughout the whole container of the fluid, no matter how large the opening. If it's open to the atmosphere, that atmosphere is going to be applying a force to that fluid, and that fluid is going to be felt all the way through the fluid. Or let's say it's like a closed container, like toothpaste tubes, right? When you have a toothpaste tube, right, and it's brand new, right, you don't have to press where the nozzle is, the toothpaste tube, to make toothpaste come out, do you? You can press all the way at the other end, right? If I have a toothpaste tube, right, I can squeeze this end of the toothpaste tube, and toothpaste will come out of the nozzle, right? I don't have to squeeze all the way over here. I don't have to apply a force here. I can apply a force here. Why? Because the force that I apply at the back, right, of the toothpaste tube, that's actually felt all the way through the toothpaste tube, and so toothpaste will come out, right? I don't have to apply force right at the nozzle. Our hydraulic brakes in your cars work that way, so that's why why you need brake fluid in your brake system, because if there's that fluid essentially allows for force to be distributed to all your brakes at once. So when you press on the brake, that puts a force on that fluid in your brake system, and immediately that force is distributed to all four of your tires immediately. Okay. And so why? Because of Pascal's law, right? The minute you apply a force to a fluid, that force is felt throughout. It works the same way as well. Like, let's say you're standing at one end of let's say you're in the United States and you're standing in New York, and there's a tube that goes from New York all the way to California, and that tube's filled end to end with fluid. And let's say I'm in New York, you're in California, and I push on the fluid of water. I push on one end of that container of fluid that one end of the fluid in the pipe, and you're standing in California, you would immediately see fluid come out your end. Even though I'm in New York, you're in California, I applied the force in New York, you would immediately see a reaction in California, because the minute that I apply a force on that fluid in New York, it's going to be felt all the way through that tube, right? Let's say this is New York over here, and this is California, right? When I apply a force to this tube in New York, fluid is going to come out this end in California immediately because of Pascal's principle. So it's how our sewer, our plumbing works in our house, all kinds of things. And it's also how hydraulic lifts work. So like we can use this idea to like increase force and help us build systems that help us utilize small forces, because of the ratio of the when pressure's equal. So what we say is that when we apply, I'm talking about force here, right? But Pascal's law is related to pressure, right? So essentially, pressure is the force per area. So the force per area would be the surface area at the top of this container, the surface area at the top of this container, right? So when I apply a force to that surface area, that's pressure, and that force per area will be felt throughout the entire container. And so essentially, the pressure that I applied to the fluid, or that the atmosphere applies to the fluid, that pressure is felt throughout the entire volume of the fluid, right? So if I have this hydraulic system where where I have this larger area versus a smaller area, I can actually use it to utilize a small force, right? Because I'll apply a small force to a small area. Now, I will have to, the depth here, right? I'm going to have to press it pretty far down to get just a very small lift over here. But either way, I'll be able to use this system to press, push down with my hand and lift up a car, right? It essentially lets me take my force and multiply it and do things with it based off the amount of area. So when we say the pressures are equal, so how does this work? How do the mathematics work for a hydraulic lift or car brakes or a toothpaste tube? Essentially what we say is that the pressure, right, being applied to one end is equal to the pressure throughout the system. So that means the pressure on one end, let's say that this is P1 over here, this is going to be equal, right here, is going to be equal to, this is going to be P2 over here. These are going to be equal to themselves. Okay, even though the force, I'm applying a smaller force and it's a smaller area, and here we're getting a larger force with the larger area, right? The pressure is going to be equal because of the difference. And so when we set up this equation where we know pressure is force per area, we see that the force per area in one side is going to be equal to the force per area on the other side. So let's say I wanted to know how, based off the area, how much force I can get applied to an object based off how much force I apply over here. Well, you're going to say, okay, F1 is going to be your applied force, how much you're pressing down, and that's going to be per certain area. And then you're going to multiply that by the area over here, and that's going to be equal to the force that's going to be applied to this area over here, right? So you can figure out, hey, if I apply this much force to this certain area, how much force is going to be applied to that other area, right? It lets you do those types of things. So it's a really nice equation. There's not much to do. You can't it's not a fancy equation. There's not, too much to do with it, but it does. It relates the amount of pressure being applied to one area of the container, showing you that the amount of force being applied to one area of the container, which is pressure, that pressure is essentially distributed all throughout the container. Okay, and because of which is Pascal's law, because of that, we say that the pressure is equal all throughout the container. So we can write this equation and we can write this relationship, and then we can look at relationships like we did here. I want to write that a little bit nicer, where we can see how much force we can actually get out of a system like this. That's what this equation is doing for us, right? Or helps us solve. Okay. And so because of Pascal's law, we can now go back to that equation that we derived over here for pressure at a certain depth, right? Or how pressure changes due to depth. And we can kind of utilize it and see how it plays a part. So we call this equation really gauge pressure. It's a gauge pressure equation. It allows us, right, if we write it in terms of the gauge pressure, it can be written like this, where You see the absolute pressure minus the atmospheric pressure is equal to the gauge pressure. And again, atmospheric pressure doesn't have to be, I mean, typically it's going to be atmospheric pressure of the earth, but atmospheric pressure is just the surrounding atmosphere, right? And so it's gauge pressure is essentially the difference between the absolute pressure, which is the actual pressure of the system, and the atmospheric pressure. It's a difference between the two, right? So what we do is we can use this equation two different ways. Now, I won't really use it this way. I'm going to use it more in the top form, the way that we derived it. But either way, this is how we use the equation, okay? So let's say that you're swimming at a certain depth, okay? And let's say you want to know the pressure at that depth. Well, what you want to do is you want to first start with the gauge pressure equation, which is what I have here. And you want to see that P2 is always going to be the pressure at which at whatever depth you're at. P1 is always going to be the atmospheric pressure. And in this case, this is going to be that constant we talked about. Remember, we talked about atmospheric pressure has a certain constant, this number right here. One atmosphere is 1.013 times 10 to the 5th pascals, right? So that's the number that you'll use in here, right? The actual constant. All right, and then P2 will be the pressure at the certain depth, and then the H, right? If we're assuming that this H up here is equal to 0, then the H at any depth is going to be some number. And so this H is going to be the depth that you're at. Right? So if you wanted, let's say you wanted to know the pressure at that certain depth, well, then you would solve this equation for P2, which would be P atmosphere, right? Added to the weight. Or if you wanted to know the depth you were at based off a certain pressure, well, then you could solve this equation for we can do it here. So what you would do is if you knew the pressure at a certain depth and they wanted to know, okay, well, this is the pressure, what depth are you at? Well, then you would solve this equation right here for H. So then that would be P2 minus PATM over rho times G, and that's equal to H, the depth that you're at. So there's two ways to, utilize this equation right here, based off what you're looking for in terms of this situation, right? Like if you're at a certain depth in a fluid, but then you can also use it for like barometers or something like that, like measuring the atmospheric pressure. So in this case, the atmospheric pressure isn't going to be equal to the isn't going to be equal to the constant. This device here, a barometer, it measures the atmospheric pressure at any time. And so what happens is that the P1 up here in this part, it's equal to 0 because what we do is we essentially fill this with mercury, which is not a volatile substance, so it doesn't release very much gas, so there's no pressure at that end of the closed tube. And then at this end, this is the atmospheric pressure pressing on the mercury, right? So that's what we're trying to measure. That's what we're trying to use this device to measure. So if P1 is 0, we can make this value 0. And then P2 is the value that we're measuring. So we can, instead of calling that P2, we can call that PATM. Because now remember, that's not the constant atmospheric pressure constant. Here, this device measures the atmosphere. So we're trying to get a measurement. What is the atmospheric pressure at this particular moment based off the change in height? And the change in height is going to be due to this tube. So this tube, right, the fluid in it is going to move up and down. All right, and based off the delta H, so let's say it was at 7 meters and then it went down to 3 meters. Well, what's the difference there? Well, the delta H in that case is equal to 4 meters, right? So that would be the number that you'd want to put in this equation. You wouldn't want to use 7 or 3, okay? So that's how you use this equation. That's how you use the gauge equation. And essentially the gauge pressure equation is the equation that also associates pressures with certain depths. And remember, I know we say delta H here, but remember delta H is any depth that the object may be at. Okay, and again, remember, why are we able to do this? Why does this work? Because, for example, for the barometer, when the atmospheric pressure presses down on this fluid like it's going to do, or on this mercury, because of Pascal's law, that force is going to be felt everywhere throughout the fluid, right? Equally, it'll be distributed equally, and so it'll cause an effect in this too that'll allow us to measure what we need to measure. And so another principle, so essentially, right there, that's Pascal's law, and that's helping us look at equilibrium situations in terms of static fluids, and how pressure essentially can change in terms of depth. But we also have this idea of Archimedes Principle, okay? And Archimedes Principle is trying to really talk about why an object floats, okay? So again, still related to static fluids, still everything, in terms of the fluid itself, the net force on the fluid is 0, okay? But, so the fluid isn't moving, but now we have objects in the fluid, right? Because we're trying to say, okay, well, what makes an object float? What makes an object sink, right? And Archimedes' principle essentially describes that principle for us, okay? And so, and it describes it through this idea of something we call the buoyant force. So let's first start with Archimedes' principle, right, and what it's trying to state. So I have it there. It says when an object is completely or partially submerged in a fluid, the fluid exerts an upward force on that object equal to the weight of the fluid displaced by the object. Now that's really, really important, but we're going to stress that a lot. So I'm not going to say too much on that definition because we're going to talk about it a lot, okay? So two things to really pay attention here with Archimedes' principle. The first one is that when the weight of the object and the buoyant force are the only forces acting on an object, and the object is in equilibrium, which means no net force, the object in the fluid, then the weight of the fluid displaced is equal to the weight of the object in the fluid, okay? So one thing that a lot of students think, the reason why I'm stressing this is that a lot of students think that the weight of the fluid displaced is always equal to the weight of the object, and it's not. That's a big misconception. It's just sometimes. And when's that sometime? Right here, when the only two forces acting on the object are the buoyant force and the weight, and then that object's in equilibrium. Now, it doesn't have anything to do with, right, this is what I say right here, no matter if the object's fully submerged or not. So the object could be floating or sink or fully under the water, or the fluid. I keep using water as fluid, but so it doesn't matter if the object's floating in the fluid or fully submerged in the fluid, right? Just as long as the net force is 0 and the buoyant force and the weight are the only things acting on that object, then the weight of the fluid displaced will be equal to the weight of the object. But that's the only time, okay? And then what's the other thing we got to pay attention to is that when an object has other forces besides weight and the buoyant force, or its velocity is changing, net force, then the weight of the fluid displaced will not equal the weight of the object. So essentially the opposite of what I said before. So when the object has other forces besides buoyant force and the weight, so if it has tension, like all other forces, I don't think I could be much more clear. Literally other forces besides weight and the buoyant force. So if it has those two forces plus more, or its velocity is changing, which means it's speeding up, slowing down, or changing direction, right? Which means there's a net force on it. Then the weight of the fluid displaced is not equal to the weight of the object, right? So that's when it's not. Essentially, right up here, I'm saying be careful because the weight of the object or the weight of the fluid displaced isn't always equal to the weight of the object. And when is it not? Well, it's when there's a net force or when there's other forces acting on the object. That's when it's not. So we're going to talk about that here because that's one of the most important confusing parts of Archimedes' principle. But I just want to make sure that it's stated and then that you have it, okay? So again, what's Archimedes' principle? It's trying to describe, right, why an object floats or not, and it's all based on this upward force, right? This upward force in the definition, and where's this upward force coming from? It's coming from the fluid. That's like the most important thing. So when people say, hey, where's the buoyant force coming from? Well, it's coming from the fluid, not from the object. Okay, so that's again another big point on Archimedes' principle. So again, when an object is completely partially submerged in a fluid, the fluid exerts an upward force on the object equal to the weight of the fluid displaced by the object, right? Not necessarily the weight of the object, but the weight of the fluid displaced, okay? So, what does that mean? Well, let's first start with the idea of deriving an equation for the buoyant force, and then we can look at the buoyant force more in detail once we understand it in terms of these ideas. So let's first imagine that we have just a cube of what? This isn't an object. You just have a piece of fluid, right? We're looking at we're imagining that we can see this chunk of fluid within the fluid. It's made of the same stuff, same density and everything. It's just we're imagining that there's this box of fluid that's made up of the same fluid in the fluid. I don't know if that makes any sense, but it's imaginary, right? It's an imaginary shape that we're saying is just made of the same fluid that is in this container. And so, what do we know? Well, we know that, and again, we've already kind of talked about this situation when we were talking about, right, pressures at a certain depth, right? We were talking about these chunks of fluid, right, with a certain area, right? So that's the same thing that we're doing here. This is just a chunk of fluid, right, that has a certain area or essentially a certain volume, right? And we're looking at the forces that are being applied to the fluid at that particular point. So we know that there's a force from the top, which would be the atmospheric pressure, right? We know that fluid itself, right, this volume of fluid that occupies this space, right, has a certain amount of weight to it. And then we also know that there's a force from the bottom, whether it's the bottom of the container or just the fluid pushing back on itself, but there's a force pushing back on the fluid from the bottom. So we know these three forces, right? Force on the top, force on the bottom way, they exist on that imaginary volume of fluid right there. And so what can we do? Well, we can write an equation to describe that, because that volume of fluid isn't moving. It's just sitting there. It's in equilibrium. It's not moving up or down or anything like that. So we can start by describing that block of fluid, volume of fluid in terms of Newton's first law, right? And then we want to go ahead and, assuming traditional coordinate systems where up is positive y, down is negative y, we say that the force from the bottom is positive, right? And then the force from the top is pointing down, so that's going to be negative, and then the weight is also pointing down, so that's going to have a negative sign associated with it. But all those, right, when we add all those things up or net them all, they're equal to 0. How do we know? Because this volume of fluid that we're looking at the forces upon isn't moving. It's just staying still. So that's how we know that it's equal to 0, right? And then we want to go ahead and just like we did when we were deriving the gauge pressure or the equation that let us look at pressure associated with depth, we want to switch the force over to pressure times area, and then we want to make sure that the mass is, we change it over to density times the volume. Okay, which is what I did here in this equation. Now, again, you don't need to know how to derive this so much, but the math is super important. And what's important in terms of the math? Well, it's just that you're seeing like the exchanges that I'm making. I'm exchanging force for pressure times area. I'm exchanging mass for density times volume, right? And so, it's very important that you're able to do these things on your own, because this is the math that you need to solve problems, okay? To solve questions that we're going to ask you. And then we also know that this volume right here, because we talked about it, is area times some displacement. And so, right, we may or may not make that exchange. We don't make it here, actually. I don't know why I pointed that out. I think I was just trying to remind you that this is true, but we actually don't make that exchange here. So what we do is we keep this equation like this, and we kind of start to state some things here. Okay, so what we do is we first bring this term over, right? We bring the weight of the object over, and we see that the weight of the object is equal to these two forces. Well, these two forces, right? The pressure on the bottom times the area, right? Minus the pressure at the top times the area. Well, that is essentially just the sum, right? It's just net force, right? We could essentially we could say these are added, and this could just be a negative, right? So it's a net force is what it is. Okay, and this net force is what we call the buoyant force. So what we do is we take this whole side and we exchange it out for the buoyant force. Now, one thing about this buoyant force is that we know that the force from the bottom is already, because you see that I have here the bottom is larger than the force from the top. And you might be saying, well, how did you know that? And it has to do with what I have written up here. I couldn't find a place for it, but essentially what happens is if we solve this equation right here for the forces on the bottom, we see that the force on the bottom is equal to the weight of the fluid plus the force on the top. Or if we solve this equation for the force on the top, we see that it's equal to the force from the bottom minus the weight of the fluid. So the force from the top, right here, is a lot less because of the subtraction sign versus the force from the bottom, which is a lot larger because of this addition sign. So we know that this side of the equation, this force, right, is going to be much larger than this side of the equation. That makes sense? And so what we do is we just make that exchange. We say, okay, well, if this is some net force here, which it is, then we'll just call that net force buoyant force, which is what we do. That's essentially, right, because when we add those up, essentially it's just going to equal one force that's going to be directed straight up, because like we said, the bottom force is pointing up, right, is directed up on this object, right? And so if the bottom force is larger, then that means when we make this sum, when we sum them, the net is still going to be coming from the bottom, still going to be pushing up. So we know the buoyant force is going to have the direction of the bottom, because the bottom is the larger vector. It's going to be the one with a little bit of magnitude left over and direction. So that's going to be pointed up, right? So what we do is we make that exchange and we say, okay, well, that's just the buoyant force. And then we see once we make that exchange that the buoyant force, this thing that we're calling the buoyant force, is equal to the density of the fluid and the volume of the fluid in grit. So the density of the fluid and the volume of fluid in the volume of fluid that we're referencing, right? So however much volume of fluid, right, and the density, that's what the buoyant force is equal to. Now, that was just to derive the buoyant force, to say, okay, where's the buoyant force coming from? We see that the buoyant, because we didn't talk about any objects. This was just the fluid interacting with the fluid pressing on itself, right? The fluid was pushing down, or the atmosphere was pushing down on the fluid was pushing back on itself, and the fluid also was applying weight to itself, right? And through that idea, we were able to derive this idea of the buoyant force. Well, we are trying to, like I said, the Archimedes principle is about objects floating or sinking. So we want to exchange this. Now what we want to do is we want to take that box that we were talking about of just fluid. We said that this is just, an imaginary box of fluid, and actually replace it with an actual object. We're going to say, okay, let's replace it with an object that actually, is the same volume as the fluid that we were looking at. But now, instead of going through this whole derivation, let's just now use our simplified version where we know the fluid is going to be applying a force to that object, which is the buoyant force, and that's always going to be applied up because the net force from the bottom is always larger than the force from the top, so there's always going to be a force up, right? And then the weight of the object, right, which is ported down, right? This picture becomes a lot easier when we're able to look at the buoyant force as just one force rather than these two forces, these two different pressures, right? One pressure from the top, one pressure from the bottom. And so, or the force associated with the pressure from the top and the force associated with the pressure from the bottom, right? And so when we do this, right, we're able to now build an equation for Archimedes principle, right? So again, this box, right, now this is a real object, right, of a certain density. Let's say it's an iron box, so it has a density of iron, right? But it doesn't have to be. It could be any type of object, right? But it's not moving. It's floating right there. It's right underneath the surface, right, but just floating. So the sum of forces have to be equal to 0 because it's not speeding up, slowing down, changing direction, or moving at all. It's a complete rest, right? Velocity is 0 of that box. And then we want to go ahead and, again, assuming up is positive, down is negative, we want to write an equation, or essentially fill in this part of the equation with our free body diagram where the buoyant force is pointing up, so it's going to be positive. The weight is pointing down. The weight of the object is pointing down, so it'll be negative, and that'll be equal to 0. And then when we solve this thing, we see that we get this interesting relationship that the buoyant force is equal to the weight of the object. What? Oh, wait a minute. That's what Archimedes' principle was trying to tell us, right? The Archimedes' principle was trying to say, hey, okay, when the object is completely or partially submerged in the fluid exerts an upward force on the object equal to the weight of the fluid displaced by that object, right? So this is kind of telling us two things, and this is a very special case, right? Remember, we said that only when the object is in equilibrium is the buoyant force equal to the weight of the object. This is the only time it's true. Okay. And when it's equal to the weight of the object, that means that the volume of fluid, what we can do is we can exchange out one side of this equation, this side of the equation, with what we know the buoyant force is equal to, which is what we derived above, that the buoyant force is equal to the density of the fluid, the volume of fluid, times gravity. And then we can make our exchange with mass, where we know mass of the object is equal to the density of the object times volume of the object. And when we do that, we get this equation that tells us that the density of the fluid and the volume of the fluid times gravity is equal to the density of the object and the volume of the object times gravity. So this is essentially saying that the weight of the fluid displaced is equal to the weight of the object. That's what this equation means. Okay, so if you start writing equations and don't get this relationship, that means that the weight of fluid displaced, because that's this side. Remember, the buoyant force is the weight of fluid displaced. Okay, so even though we're calling it all these things, okay, what you need to have in your head, what you need to memorize and store up there, is that the buoyant force is the weight, the value of it, okay, whatever it's equal to over here on this side. So this is the buoyant force here, but whatever it's equal to, which will be this side, whatever this side of the equation, is what the volume of the weight of the volume of fluid displaced. No matter, it looks weird. It's like, but that's density times, that's density of the object times volume of the object. Carl, that doesn't look like weight of the volume of fluid displaced. But what you need to understand is that's what the buoyant force is. The buoyant force is a measure. It gives us a number of the weight of the fluid displaced by an object that's in that particular fluid. Okay? So even though we're able to write this relationship with the buoyant force, it might be better to get rid of that and say that the buoyant force, right, when things are in equilibrium, when the buoyant force and the weight are the only object or the only forces acting on the object, and the buoyant force is going to be equal, right? Or how much volume of fluid displaced is going to be equal to the weight of the object. That's what this is trying to say. So let me, actually, that top equation says what I want to say. So I'm going to write this back. Because if we know, now again, we can say a lot of things about the buoyant force, but one of the definitions, the straight up look in the book, see what the definition is that the buoyant force, the value of the buoyant force, when you get the number, whatever this number is on this side, it's going to be the weight of the fluid displaced. And in this case, it's the weight of the object, but it's not always that, only in this equilibrium situation. Okay, so if you're not understanding, you will here in a second. All right, so just to restate what we're saying. So the buoyant force, right, is the total force on an object due to a fluid. Okay, the buoyant force comes from the fluid. It's just the force from the fluid on the object. That's all the buoyant force is. What are the things we have to pay attention to? Well, first of all, that the buoyant force is always equal to the weight of fluid displaced, which need not be, this is very important, this slide, which need not be the same as the weight of the object, okay? So we just saw, you might just say, but Carl, we just derived this equation that said that the buoyant force is equal to the weight of the object, so that means that the fluid displaced is going to be equal to the weight of the object. But that's only for this situation where we have only the buoyant force and the weight acting on the object, okay? When we look at when there's more going on, so like in this case, the object's accelerating up, which means it's speeding up. Imagine this is like a beach ball or something that we put under the water, right? Well, the minute we let it go, it's going to shoot up, right? So even though the buoyant force and weight are the only things acting on this beach ball, it's speeding up as it's moving up. So there's some inertial force, there's some acceleration there. Okay, so if we wanted to describe this situation, right, in terms of describe the motion and relate the motion to the forces, we want to start with Newton's second law because it's speeding up, right? We know it's speeding up, right? Displacement, acceleration in the same direction, which means what about the buoyant force? It must be larger than the weight, right? Because it's pushing it up, right? It's the net force here, right? And so what do we do? Again, assuming up is positive, down is negative, right? Buoyant force is going to be positive, weight is going to be negative, and then that's going to be equal to ma. Now remember, this ma, the mass is the mass of the object. It can't be the mass of the fluid. The object is the thing that's speeding up, not the fluid. So that's what the mass on the others, in terms of ma, the mass in ma is related to the mass of the object. Now, once we have this equation here, right, all we're trying to do, now we can do a lot of things, but I have other videos showing you how to do that. This is just trying to show you that how when the buoyant force is not equal to the weight of the object, okay, or essentially when the buoyant force, which is the amount of the weight of the volume of fluid displaced, is not equal to the weight of the object. So sometimes the volume of fluid displaced is equal to the weight of the object, but these two cases and other cases like these that I have in front of you right now is when the volume of fluid displaced is not equal to the weight of the object. And how do we know? Well, when we solve this equation for the buoyant force, which is the weight of the fluid displaced, we see that the buoyant force is equal to the weight of the object, right, which is this part right here, plus mass times acceleration. So it's not just the weight of the object. We see the buoyant force isn't equal to just the weight of the object. So that means that the volume of fluid displaced is equal to more than just the weight of the object. That's what this equation is telling you. Okay, and the same thing over here. Even though this thing's at equilibrium, this box isn't moving. It's attached to a rope, and this rope, right, is, let's say, attached out out above the water, right? So there's tension in this rope, right? Because the object's pulling down. And then because the object's in the water, there's the buoyant force. So we have these three forces, but the object isn't moving. It's just sitting there in the water. So because of that, since it's not speeding up or slowing down or changing direction, that means that Newton's first law applies, right? And then again, up is positive, right? Down is negative. So the buoyant force and tension are both positive, and weight pointing down is negative, and those are all going to be equal to 0. Now again, what's the point of this? Just to give you another situation of where the buoyant force is not equal to the weight of the object, or where the volume of fluid displaced, the weight of the volume of fluid displaced is not equal to the weight of the object. So when I solve this equation, I see the buoyant force is equal to the weight minus tension. So again, here, the buoyant force isn't equal to weight, which means the buoyant force is not equal, right? The volume of fluid displaced is not equal to the weight of the object. It's equal to mg minus tension. That's what the volume of fluid, the weight of the volume of fluid displaced is going to be equal to, mg minus tension, okay? So that's how it works. And again, what is this for? Again, just trying to show you that the buoyant force is not always equal to the weight of the object, but is always equal to the weight of fluid displaced, right? It's always equal. The buoyant force is always equal to the weight of fluid displaced, but the weight of fluid displaced might not always be equal to the weight of the object. And that's all that's trying to show you, okay? And that's what this caveat essentially was stating. And then the second one is that the buoyant force depends on the density of the fluid and the submerged volume of the object, but not the density of the object. So essentially, like, think of like a giant aircraft carrier. Those things weigh tons, like so much, right? But they float in the ocean. Why? Well, that's because it's filled with air, right? So essentially, the relative density of the ship is less, right, when compared to the density of the water, even though, yes, it's made of steel, but the density per volume ratio, that's what I meant to say. I'm so sorry. The density per volume ratio, right, is equal to that of water. So if something's floating, let's say it's a really, really heavy object. Well, this, right, the density per volume of water is going to have a certain number, right? And if the object, right, is equal, these two, if the density per volume of the water is equal to the density per volume of the object, then the the object will float, right, or essentially float right underneath the surface of the fluid. But if it's less, right? What if the density per volume of the object is less than the density per volume of the fluid? Well, then that means it's going to float. That means it's going to float, right? So even though you might have this massive structure, if the density per volume is less for that object than the density per volume of the fluid that it's in, doesn't have to be water, then the object's going to float. And that's what this caveat's trying to say, is that the buoyant force depends on the density of the fluid and the submerged volume of the object, but not the density of the object. The density of the object doesn't matter, okay? The ratio matters in terms of the ratio in comparison to water, but it's really about the volume of fluid, the volume of the object in the fluid, or the volume of submerged object in the fluid, and the density of the fluid. Okay, and so what does that mean? I'm going to erase this because I have all this written here that I want you to pay attention to. Okay, so essentially, what is this caveat trying to tell you? Buoyant force depends on the density of the fluid and the submerged volume of an object, but not the density of the object. Essentially, that when the density of the fluid is greater than or equal to the object, it's going to float. But when the density of the fluid is less than the object, it's going to sink, because it has to do with the density of the fluid, not the density of the object, but the density of the fluid. okay? And then when the volume of the fluid is less than or equal to the volume of the object displaced, it's going to float, right? So when the volume of fluid displaced is less than or equal to the volume of the object, it's going to, right? This is volume of fluid displaced, right, is greater than or equal to, and this right here is the volume of the object. It's going to float. But when the volume of fluid displaced is greater than the volume of the object, then it's going to sink. Okay, so that's essentially the relationships you need to have in your head to understand this idea. And just to take it one step further, that's what these relationships are trying to show you here. Okay, so for fully submerged objects, what we know is that the volume of the fluid displaced is equal to the entire volume of the object, which makes sense. If the entire volume of the object is in the fluid, then the amount of fluid displaced is equal to that entire object, because that's how much fluid has to get out of the way for that object to be in the fluid, right? The fluid and the object can occupy the same space at the same time. So the fluid has to move out of the way to make space for that object. And if the entire object is in the fluid, then the amount of volume of fluid displaced is exactly equal to the amount of volume of object in the fluid. But if it's floating, it's not. It's just a ratio, right? When it's floating, then the volume of the object, or the volume of fluid displaced, is only equal to the amount of the volume of the object in the fluid. Now remember, don't get confused here. This has nothing to do with the weight of the volume of fluid. We're just talking about the amount of volume, okay, in terms of the measure of volume. Okay, but remember, in terms of the buoyant force always is equal to the weight of volume of fluid displaced. Okay, but in terms of looking at just a volume to volume ratio for fully submerged objects, right, it makes sense that the amount of fluid displaced is equal to the entire volume of the object if all that object is in the fluid. Where if it's floating, the object's floating, then however much of the volume of the object is in the fluid is how much volume of fluid is displaced, right? Because why would the fluid only has to make room for how much of the object is in that fluid, right? The atoms of the fluid have to get out of the way for the atoms of the object. So the more and more of the object that's in the fluid, the more and more atoms have to get away, right? Get out of the way so that object can be in the fluid. And when the object's fully in there, then the entire volume of fluid that got out of the way is equal to the entire volume of the object. But if only like half the volume of the object is in the fluid, then the volume displaced is only equal to half the volume of the object, because that's how much fluid had to get out of the way. Only half, right? Only as much as the amount of the object that's in the fluid. So I hope this was helpful. I know it was long, but this is a lot to talk about it. It's a lot of information, but just keep in mind what we talked about here, right? A few different things. We talked about, pressures at certain depths, Pascal's law, right? Using the gauge pressure equation, Archimedes principle, and looking at the buoyant force, right? We're really trying to understand how all these things go together in terms of static fluids. All right, so I hope you enjoyed everything. I'm super proud of you. Keep in mind this video does go with fluid flow, so hopefully you're off to watch that one next. And I'm super proud of you. And if you need anything, be sure to reach out to any tutors or your professor or anyone you need. I am incredibly proud of you, and I will see you on the next video.